In the previous lecture, we considered a problem of solving exactly a field theory with a quadratic Hamiltonian and a linear coupling to the external source. So our goal was to compute the generating functional, which is basically the only information we need if we want to compute all correlation functions, provided we can compute the generating functional analytically, of course. And this was defined in the following way. There was a negative Hamiltonian, there was a Hermitian operator defined in terms of fields that we identify with the Hamiltonian that appear with a negative sign at the exponent and a negative source term which I symbolically represent this way. And H naught is a functional of the field and was defined to be 1/2 dx phi of x w phi of x, while the product was nothing but the integral between the source and the field. And finally, the operator W was whatever Hermitian operator you can think of. In our specific case, we focused on the following particular case, but you can generalize this to more complicated number of derivatives. The only request is to have at most 2 powers of the fields entering in the definition of the Hamiltonian, because this request makes this integral of Gaussian type. Finally, in this specific example, we define the Green's functions, and I'll focus on the 3-dimensional case. And the Green's function was defined as a Yukawa type of function. Now, with these definitions in hand, we arrived to a very, very, very important result, which was that the generating functional could be written as an irrelevant term, which is the generating function evaluated at zero external source, times 1/2 j w j, where with this notation I really mean the double integral with respect to x and y of 2 sources term, j at x, j at y, connected, with the Green's function, w to the -1, or better, delta. Now, you can physically interpret this formula by saying that the shift, now if I remember that the partition function is related to the free energy, I can relate this to the shift in free energy associated with switching on an external source. Right? So basically delta G is, for this formula, negative 1/2 J delta J, which basically is telling you how much free energy, how much you lower the free energy by switching on a paramagnetic system by switching on an external magnetic field. But this course is not so much on this lecture is not so much on the physical thermodynamic interpretation of this formula, but rather on their implication for computing correlation functions explicitly. And we're going to start doing examples. So first of all, let's consider the trivial cases. So today we begin by doing some examples and then we draw some general rule. So examples. Well, the simplest case is, of course, the magnetization. To get a magnetization, all we need to do is to take the negative of the derivative with respect to the source in a point of E 1/2 J delta J and divide by itself, E to the 1/2 J delta J. Notice that I did not include the partition function at zero source because it appears in the same fashion upstairs and downstairs. At the end of the calculation, we should remember always to set the sources to 0. So let's do this differentiation. Well, when the functional derivative acts on the exponent, of course, it leaves it as is, and it acts on, and all it does, it provides a prefactor which corresponds to the derivative of the exponent. Now let me write the exponent explicitly. I have two integrals over dy and integral over dz of j of y delta of y minus z j of z. So let's evaluate this quantity. Well, this is two terms. I'll be pedantic the first time so that everything will become clear. And then maybe next times we come across similar evaluation will be faster. That's the functional derivative of j of y divided by j of x, delta y minus z, j of z. And then I have a functional derivative dy dz, and then I have j of y delta by y minus z, and then delta by djx of j of z. Now, remember our result that we had last time, one of the last lectures. I will copy it down here. That dj of z versus dj of x is delta of z minus x. Remember, if you are not, if this equation looks mysterious to you, the best thing to do is to discretize, in which case the value of the field in each point becomes an independent variable, and then clearly, 1 second, ciao, 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 my son saying goodbye for his celebrated, well, long expected 200-meter walk that finally we are allowed to take in Verona after many weeks of total restriction. I was saying, when you discretize this formula, then the value of the fields in different points are independent variables, and this becomes really a ordinary derivative, which of course will provide a simple Kronecker delta. When you generalize to the continuum, you get a function of delta. So if you do this, then I don't know how to put it. I should. If I do this, okay. If I do this, here I will get a delta function here. So let me just replace it with a delta function of x minus y, and I will get a delta function here, delta function of z minus y. And now here I can use this delta function to get rid of course, one of these integrals is over z here. I will get this delta function to get rid of the integral over y. So I will remove y, and everywhere I see y, I will put x. And I will use this to get rid of the integral over z. So when I will see z, and whenever I see z, I can put x. So in the end, the result, I get twice the same quantity, because up to a change of variable, given the fact that delta is symmetric and is an even function, since it's a function of the modulus, then I get twice the same contribution, and the result is trivially integral over y, j of y, delta of y, x minus y. And I would like to emphasize that this equation really looks very much like the electrostatic equation for the fields, which is the source term for the fields convoluted with the Green's function, which in case of Coulomb is simply 1 over r, right? This is in electrostatic. In the electrostatic, we know how to solve for the field by taking the convolution of the source term, in this case is a charge density, with its corresponding Green's function of the equations, which in the absence of mass terms in the definition of W is simply Coulombic. You know that if you take a Yukawa potential, you send the mass to 0, you get the Coulomb's potential. So basically all this is telling me that it's quite the analog thing, as it should. So that's it. But then, you know, in the end of the day, so what we've been showing now is that basically this is nothing but negative. The negative comes, and I don't think there is a negative here. Yes, there is a negative. I get a negative of this convolution. But then I'm bound to set the sources to 0. And of course, after I set the source to 0, this term will be trivially going to 0. Because it's proportional to the source. So when I set the source to 0, the magnetization goes to 0. And that's not a big surprise, because we are, after all, in a paramagnetic system. And in a paramagnetic system, there is no magnetization by default. Okay, good. Let's do one more example. Well, we'll do a couple more examples. The next example is the two-point function. And I define this as second derivative with respect to x1. I will put a plus now because I have two negative signs, one for each derivative, so I will not forget, or I will not have to worry about this. Let me make some space for it. Thanks. Okay, that's what we want to evaluate, right? Now we can go quick because we have learned basically how to do this when we act on these derivatives, and of course, again, the setting the sources to 0. We get, let's first act on this. We get 1 over e to the 1/2 with my notation j delta j. Then I have d by dj in x1, and now I perform the derivative with respect to j2, and I will get 1/2, and then I will get j delta, so to say, evaluated in x2, right? Plus 1/2 j delta. So basically twice j delta. That's what we just calculated. And then, of course, I get again my exponent 1/2 j delta j, and I don't have the 1/2 anymore because I have two terms of the same general kind. And in the end, I should send the sources to 0. Now, when I act with the second derivative now, I have two options. I can either act on this j, right, which sits inside an integral, remember, or I can act on one of these j's. So what I will get in the first case, I will get delta of x1 minus x2 and no j's because I've killed this j, and then these two guys will cancel it. When I act on here, I will kill this j, right? It will become a delta function. So I will be left with a delta. And this exponent will cancel out with this exponent. So the first action will result in just in delta x1 minus x2. But then I have another term which survives, and is the one where I act with j, with this functional derivative, again on the exponent, in which case I will get a delta j squared, so to say, right? And then the other terms will cancel out. Now, when I eventually send the sources to 0, then clearly the second term will disappear, but the first term will survive. So what we've been able to demonstrate with this calculation is this fundamental result, which is very, very, very important in field theory. Let it be statistical or quantum field theory. Okay, given a quadratic theory defined by some operator W, then the two-point correlation functions defined as usual actually is the inverse of the operator entering the definition of the quadratic Hamiltonian. That is the Green's function of W operator, which is basically W minus 1. Remember, this is true only if the Hamiltonian is quadratic in the fields. So this is a result that tells us something quite important. It tells us that two-point functions are in fact Green's functions of the quadratic operator. But this is true only for quadratic Hamiltonian. Now, those of you who have taken field theory, quantum field theory, will recognize these results, because in field theory, your free theory is a quadratic theory with a Klein-Gordon, for instance, Lagrangian or action at the exponent. And then what you have is that the Green's function is in fact a time order product of field operators, right? Where x now and x2 are space-time points, right? This is in quantum field theory. In statistical field theory, we have an analog expression, but rather than having a time order product and expectation values on the vacuum state, we have thermal averages, and there's no time order because, by the way, there is no time at all in statistical field theory. That's in statistical field theory. Of Of course, there's no need to know quantum theory to follow whatever I say. Just stick to the second one if you haven't taken quantum theory. Just trying to draw an analogy for those who are building their experience in quantum theory so they can use this course as a reinforcement for their education in quantum theory. I think we have an important result coming up here, and I think we will be using this many times. It's a building block basically of Feynman diagram techniques, but we'll come to that in shortly. So as a last example, let's now consider, I think some generalization. From what we did, it is clear that anytime we have a quadratic theory and we act with 3 functional derivatives, we always have the result depending on a finite number of source terms, so that when we send the sources to 0, then the source term kills the result. So we can generalize this by saying that correlations with any odd number of points are all 0 in a quadratic theory. And anytime something is a universal result in a physical theory, it's 99.99999% of the time the result of a symmetry. And the symmetry here is obviously this inversion with respect to the direction of magnetization. The Hamiltonian is quadratic. If you have in probability theory, you know this already, but even in mathematics, you have n to the odd powers of a Gaussian. This is always 0 by symmetry, because it's the integral of an odd function, and this is an even function. And that's basically the mathematical reason behind this general result. On the other hand, when you have an even number of fields, like 2 or 4, there is only one term that eventually survives, not one, but only one type of terms that eventually survives after you act with a functional derivative with respect to the sources. And the terms that survive are those in which you kill by functional differentiation all the source terms and you're left only by product of propagators. So in particular, let's consider the simplest case, phi to the 4th. And then in this case, I have phi x1, phi x2, phi x3, phi of x4. Now that's a little bit of a complicated calculation, and graphically this is represented by putting 4 points joined to a block, right? Remember. There's an x4 in here. Right. So suppose we want to evaluate this. Then again, it's a bit boring, and it's the last one we do, I promise, but I think it will make the point clear. Unfortunately, this is things you do in class. When you are in class, you give the exercise to the students, and then you try to guide the students to do them themselves so that this becomes more active as a lecture than it is by remote. In a remote setting, I have to do it myself in front of you, and it's a little bit more boring. But okay, that's part of the game of being locked down. So that's what we want to do. Now we have 4 functional derivatives with respect to j. And what I want to do is, rather than doing all these lengthy calculations, which would take me probably an hour or so, is to try to use some kind of general argument to guess what the result will be. And I also want to notice that I can even get rid of this denominator factor if I remember to set the j at the end, because it will give me a factor. No, I think it will give me a factor 1/2. No, it will give me, when I set the j is to 0, this exponential factor will disappear anyway, so I don't even have to worry. Now, let's look at what happens. I have 4 functional derivatives. When these 4 functional derivatives will act on this exponent, they will drop a factor j. Now, when the second derivative acts, I have 2 options. I can even act on the j, or I can act on the. So after the first derivative acts, I have something like j dot delta e to the 1/2 j dot delta dot j. When the second derivative acts, that's after one derivative. When I act with the second derivative, I will get j dot delta squared. So I'll put 2 here. And then I get 1 j delta j. Okay. When I act on the third derivative, I will get, and I will get also, acting on the second derivative, I will get also a term like delta e to the 1/2 j delta j. When I act with one more derivative, from here, I will get, oh, now it's getting cumbersome to fit everything in the screen. Let's see, I go from here up. Let's see, I go from here up, and I will get like a j delta, j delta, j delta. Then I will get when I will, that's when then I will get a j delta delta e to the 1/2 j delta j. That's when I act here. And I guess I get 2 of them. Then I will get a term in which I will act here, and I will get j delta j delta j delta e to the 1/2 j delta j. That's when I will act here. And finally, I have the terms where I act here. And this will be delta j delta e to the 1/2 delta jj. That's when I act on this part. And I get 0 when I act on the functional derivative here. So I don't get anything else. Now I'm left with the last functional derivative. But now you see that not all of these terms can survive the last action. So the only hope I have to get a final result from calculation is to kill the right number of sources with derivatives than I have in my calculation. Stated differently, if I have too many functional derivatives, then I eventually end up to a situation in which I have a functional derivative of a product of correlators, and this will give me 0. Because I don't have any source to kill here by functional differentiations, right? So the functional derivative here will give me 0. So this term will have no contribution. And on the other hand, when I act with too few functional derivative on the prefactor, which means that I'm acting too many times on the exponent rather than on the prefactor, I will end up with terms which have a bunch of deltas, but maybe some residual j's. And when I send the j's to 0, these will be killed too. So it's kind of funny to find out what they are, right? For instance, let's look at this. This has no hope to survive because I have one functional delta left. Terms of this type, I don't have hope to survive because, terms of this type are those who can give me a hope because I can act and kill this delta with the last action of my field. So these are okay. What about this? Clearly they don't have hope to survive. But there are some hope also from here, because if I act on the prefactor, I kill this, so I will survive. So there will be two contributions that will survive. One from here and one from here. Now, if you do things carefully, which it would take you maybe 1 hour the first time to do it properly, keeping track of all the indices. I've been admittedly sloppy here. I didn't keep track on the x1, x2, all the indices that appear in this calculation. I just wanted to give you the general structure. If you instead do things properly, you discover that the two terms that remain are the following: delta x1, x2, delta x3, x4, plus delta x1, x4, delta x2, two already used, x1, x plus delta x1, x4, delta x2, x3. So, do things carefully and you find out this. And if you graphically represent this in our blob, you'll discover that my 4-point function, x1, x2, x3, x4. Now, if you choose to represent delta of x, y as a line collecting x to y, then you can show that this blob can be represented in this form. x1, x3, x2, x4, x1, x2, x3, x4, x1, x2, x3, x4. Now, each of these three terms corresponds to a different way of forming pairs out of the even number of points in the correlation function and replacing each pair with a corresponding 2-point Green's function. So the rule that we discovered by inspection, and it can be generalized by induction, is that if you have a quadratic theory, not any theory, just a quadratic theory, because we're using the evaluation of the partition function, which only holds for quadratic theory, and you have even number correlation functions, all you have to do is to form all possible ways of joining pairs, saturating all the points of the 2-point function, all the different ways of connecting topologically connecting the extremes of the two-point function, and replace this connection with a line. Using a more field theoretical language, we have learned that the Gn is the sum of all possible contractions. And the word is take a pair and join it by a line. And that line will represent one factor of, in this case, delta of x1 minus x4. In this case, delta of x2 minus x3. In this case, delta x2 minus x1, and so on and so forth. So you have to find all possible contractions, sum them up, and replace each line with a two-point correlation function. This is a result that is well known in field theory, let it know quantum or statistical field theory, and it's called the Wick theorem. Now, the Wick theorem is very hard to prove in quantum field theory in canonical formalism, but you can re-demonstrate it by reminding yourself that, say, now this is a side part of the course for those coming from field theory, that you can define a generating function for this time order correlation function in quantum field theory. And in this specific case, this would be the exponent of I over h bar, the Klein-Gordon action, which will be phi of x. Now I'm not sure, well, I use delta Lambert, phi of x times e to the I over h x j of x phi of x. And now your functional derivatives trick will work exactly the same, except that this time you will have highs to take care. So your functional derivatives will contain like negative I over h bar factors to take care of. Or minus 1. But it will work exactly the same, and they will give you a prescription to find out ways to calculate time order correlation functions of any product of fields as contractions of two-point time order correlation functions, that is the propagator, the Feynman propagator for this quantum field theory. So the Wick theorem translates from statistical field theory to quantum field theory in a trivial way. And just for you to know, Mr. Wick was an Italian professor from Turin, so he kind of gave a fundamental contribution to field theory from Italy. Okay, so this is the last part of this lecture. We now have a tool that allows us to compute anything we want for two-point function, for correlation functions in a quadratic theory. So we are in an analog situation of when you completely solve the harmonic oscillator. And this is not by chance. The harmonic oscillator, if you think about it, is a field theory, quadratic field theory in 0 plus 1 dimension. What do I mean? Now, what is the harmonic oscillator Hamiltonian? It's, well, you can define it to be negative x d by dt squared of x plus 1/2 omega squared m squared x squared. I use the integration by part here when he enters into the action, right? The kinetic energy part, so, okay, let me be more precise. The path integral for the harmonic oscillator would be, something like, the generating function for the harmonic oscillator would be j of x, integral over dx, right? And then I have an I over h bar, and then I would have an integral over time of x dot square. And I write this as using integration by part in the following way, and then I will have my potential energy terms. So this is the action of x. Sorry, and of course here I have x, not phi. Now, if you define phi of x in 0 plus 1 dimension, where 1 is time, and I rename this becomes phi of time, because there's only time, and I rename this to be x, I get exactly this expression. Right? So this is telling me that quantum field theory, scalar field theory, is quantum mechanics is basically quantum field theory in 0 plus 1 dimension, where 0 spatial dimension and 1 in time. But this is just a curiosity for you to know. But this is just to say that I went through this digression to say the fact that we are in an analog situation of the harmonic oscillator, we can compute anything we want and we have analytic results. So we kill the theory. We are in an analog situation here with Gaussian quantum or statistical fields, but this is by no means coincidence, because Gaussian path integrals, the harmonic oscillator theory is a special case of a theory with a Gaussian path integral. So we have generalized the result we learned from, say, third year in college, when we learned about how to solve the harmonic oscillator to more dimensions, and that basically generated field theory. Okay, the last arguments I gave are a little bit perhaps can be confusing to some. You can forget about them. They're not essential for understanding the course. They're just kind of thinking over what we did for those who have a broader perspective and like to connect different parts of their knowledge. Okay, of course, we said nothing about non-quadratic Hamiltonian. And most of, if we could only do harmonic oscillator, our physics knowledge would be very limited. There's only very limited systems that can model with harmonic oscillators. So what to do when the theory is more complicated than that, that's challenging. And that's what we will discuss in the next several lectures. Okay, bye-bye.